Let's look at an example of how the precision of various estimators, so x hat and y hat, behave. Suppose we have 3 observations of a value y in meters as a function of time t. The observations are made at times t is 1, t is 4 and t is 7 seconds. We show the observations in this plot. The observations have a measurement error with sigma 0.5 meters. We visualize this here with the 2 sigma error bars. If we are interested in the parameters of a linear model based on these observations, the mathematical model looks like this, where the vector of unknowns includes an offset, which is x1, and a velocity, which is x2. And using the best linear unbiased estimator equation, we find the best linear model through these observations. We indicate this here with the green line. Let's move this plot to the top. In this plot, the adjusted observations, the y hat values, are indicated by the little green circles. Mathematically, we find the estimator as y hat is a times x hat. Now we are interested in the quality of the adjusted observations y hat. To express this in a covariance matrix, we use the error propagation law for variances to get the qx hat. We will now try to visualize the content of the important matrices. The qy matrix is a diagonal of dimensions 3 by 3, because we have 3 measurements, with variances 0.25, because the standard deviations were 0.5. The A matrix is a 3 by 2 matrix, with the times 1, 4 and 7 seconds on the right column. And the qx hat covariance matrix tells us that the precision, or the variance, of the offset of the line is 0.31. This is meters squared. That is a standard deviation of 56 centimeters. The variance of the velocity is 0.01 meters squared. Meter per year squared, I should say. That's a standard deviation of 10 centimeters per year. There is a covariance between both terms, which means that the offset and the velocity are not independent. To find the quality of the adjusted observations, y hat, we apply the propagation law of variances one more time. This gives the covariance matrix of the adjusted observations, qy hat. If we evaluate this matrix, we find this matrix on the right-hand side. Focusing on the diagonal terms, it shows us that the precision, or variance, of the first and last adjusted observations is larger, or worse if you like, than the precision of the middle parameter. Moreover, it shows us that all 3 adjusted observations, that's the green circles in the upper graph, are correlated, since the off-diagonal terms are not equal to 0. We show this by drawing the 2 sigma confidence intervals with the red lines in the upper plot. This result tells us that the adjusted observations at the beginning and the end of the time series are of poorer quality than the middle one. Let's look at the effect of having more observations, or observations with a higher precision. The top figure here shows the results we have just obtained for 3 observations with a standard deviation of 0.5 meters. The middle figure uses more observations, 7 in total. It shows that the red 2 sigma confidence intervals are a bit smaller than for the case with the 3 observations. Therefore, it makes sense to include more observations. Finally, the lower figure shows the case in which there are also 7 observations with a standard deviation of 0.25 meters, so the half of it. This also narrows the confidence intervals of the adjusted observations. With this example, we conclude the section on the interpretation of covariance matrices.